Good evening, fellow researchers, and welcome to the third installment of our Igniting Research Passion series, where we will be navigating the topic software-defined network traffic management. As you may have guessed from the title, this topic will be dedicated to guiding future and fellow researchers through analyzing, interpreting, and learning about the centralization and management of network traffic. Dr. Madhurima Ray, who will be leading our session today, is an associate professor of computer science at the University of Pennsylvania. With both an impressive academic and industrial background, from learning various subjects encompassing network and database management, computer organization, and most notably, having an array of expertise in various storage systems, and on top of that, working in notable companies such as serving as a software engineer at Dell EMC and interning at HP, Dr. Madhurima is the perfect speaker to guide us through the topic today. So without further delay, we invite Dr. Madhurima Ray to lead the session now.
Ma'am, you are muted.
Sorry. Yeah. Thank you so much. Thank you, Ashna, for the nice introduction. I would like to get started. I'm starting with this idea that you might, like most of you might not have any background in software-defined network, but if you think that that's not needed, then I can step back and directly jump into traffic management issues. Okay. Just let me know, like, what is your comfort and what I can skip and what you're already aware of. Okay, I'm happy to accommodate the changes accordingly. Okay, so today we are going to discuss about the software-defined network, and I'm trying to pinning this. This one. So pin this one. Okay, so today we are going to talk about the software-defined traffic management in the context of the software defined network. Okay, so to start with, I would like to give you some ideas. So this came out of an academic project around 2020, and then people started to realize the advantages of it, and now all it is. So the hardest part in adaptation is because most of the computers are still running on the TCP/IP legacy network, but people are getting to understand the utility of using SDN over TCP/IP. So we will start with the definition of what is software-defined network is, which is an abbreviation, or SDN is an acronym for the software-defined network, and then we will move with the comparison between the traditional network architecture and the SDN, and then we will discuss about majorly. I have classified four types of traffic management that we are going to talk about, like what are the challenges. And most of the time, I do not say it's a challenge. I talk about them as an opportunity, because wherever there is a challenge, you always get an opportunity to explore and work around that problem, right? So I refer to those challenges as an opportunity for research. Okay, so what this is an overview of what we are going to talk about. So it will have the infrastructure, how it look like, then the comparison between the traditional network versus the SDN, and then the pros and cons of the SDN traffic management. Finally, we will talk about some of the solutions, like not like the research paper wise, like this paper has talked about this solution, but overall, what are the type of solution that have been proposed and what are the shortcoming of them. So what is still left to be done, and you can pursue whatever that you feel like. Okay, and finally, I'm going to conclude and I'll wait for QA. So I'm not sure how you do the QA. It could be at the end of it, but I'm very fine to answer your question. I'll try to look through the questions, or if someone is raising hands. But if somebody can take that responsibility and let me know if somebody has a question in the chat or raising hand, I'll be happy to accommodate during the presentation even. Okay. Okay, so what is an SDN? So if you see this picture, this is taken from the paper called Software Defined Networking Architecture, Traffic Management, Security Placement, a survey. So if you see this, you see, this is the structure of a traditional network where each switch or the networking device is responsible for two things. One, control. Next, data. That is, we call it control and forwarding. So what is control? So when a packet reaches to a network switch, the network switch has to decide two things. First, which direction the packet has to be forwarded, and then physically forwarding the packet to the direction. And it just has a short-term visibility. So how it every switches or router defines which way to forward the packet is they will have a routing table. They will look up to the table, and it will tell that router or the switch that this interface it should forward the packet to. It's just a single hop that it looks for. Like if I want to go from this switch to the next switch, which way I should go. They do not look into the whole path as to see if there is any congestion going on somewhere down the path. If I'm forwarding in this direction, I should not forward in this direction, else I should forward in this direction, some other direction. So that visibility is lacking. Okay. Now, what we moved out of, like when we moved out of the traditional network, we moved to the software defined network. What the software defined network does, you see, there is a clean separation between the controllers and the programmable switch, right? So why we are saying the programmable switch? Because those forwarding instruction, like which way to forward, is been fed by the controller here. So there is one central entity we call the controller, which is more like a server that takes care of this decision making. So somehow, I'm not going to talk about right now how, but somehow this guy, the controller, can build a global visibility over the network. It can see what's going on throughout the network, anywhere in the network. Okay. For simplicity, just assume for the network there is only one controller, and that can see what is going on throughout the network. So what it's going to do is it is going to define when a packet reaches a particular switch, which way it should direct if the destination is this, right? So if the source is this, like if the current switch is this and the destination is this, then which way the packet has to be routed. It happens at a really fine grained level. It happens in the flow level, and I might be talking a little bit in detail about that, but not too much. Okay, so just to give you a simplistic idea, is the controller is the one who would define which way a packet should travel, and all that the switches has to do, you see the programmable switch, which is blue in color, all that they have to do is to, when a packet arrives, they will do a kind of lookup table thing. So you understand, everyone, what is a lookup table? That it's kind of a match. So they will have a lot of options. So they will look for a perfect match for this packet. If there is a match, it will find out what is the rule set for that. It's somewhat similar to the key value or some dictionary that you use for Python. I believe most of you have used the Python dictionary. It's very similar. So it will look for a perfect match. If there is the match, it will pick up the rule and it will forward the packet to that direction. Okay. It does not really use the brain. It is just an entity that do the physical work of forwarding. That's all. There is no brainer for this job. Okay, to the programmable switch, this is no brainer. It is just going to follow whatever being dictated by the controller. Just give me 1 second. So Varsha, I have a question. One of my students is trying to get into this. So should I just give him the Google Meet link?
Yeah, ma'am. Yeah,
okay.
ma'am.
Okay, just give me 1 second. Sorry. Yeah, sorry for the interruption.
That's okay, ma'am.
So he is an intern who worked with me at Intel. So he's currently working at or doing his PhD at Georgia Tech. His name is Hamid, so he will be joining. Okay. So this is what the difference between the traditional network versus the software-defined network. And this interconnection, like how this controller should communicate to this programmable switch, is dictated by a protocol, standard protocol, which is called open flow protocol. Anyone here have heard of this, like open flow protocol? Now, why this is set? Because you need some standard rule for communication. Like when you do this TCP IP protocol, they set up those rules, right? How you implement that is a different story. Here, what is needed is there is some standard. So even if you buy a Cisco switch or a Juniper switch, it doesn't matter. When the protocol is implemented, they should do similar stuff. The implementation is independent of the standard. There are standards they have to follow whichever way you are implementing. Okay, so the communication that they use for this is called open flow protocol, and that is very standard. Okay, there's like no like I would say like there would be another section that you will see that you can use any type of programming, but for this controller to switch programming, you must use the open flow standard protocol. Why we have moved or why we have decoupled this makes a lot of sense in terms of programmability. Like the controller can now tell the switches if there is anything that went wrong along the route. If that happens, then the controller would just go and change the forwarding rule, the existing forwarding rule, with something new at the runtime. Okay, so on the fly, the controller can change the routing law. We sometimes call this as flow rules, and each switches will have a flow table that stores the these rules. Okay, so any question before I move to the next? Any idea you need to know before I move to the next slide? Okay, I don't see any question. I don't see a chat window actually. Okay, there is one due to some reason. Okay, so we divide the software-defined network in these three sections or three layers. We call this layer as the infrastructure layer, or this is where exactly the forwarding element stays, like the routers, switches, and everything. There is the control layer, which is responsible for programming those forwarding devices. And then there is an application layer, which is the one that uses this SDN network. Okay. Now, see, there is one interesting fact. This controller would have a visibility, or we call it a global visibility inside the network, right? But this is a single point. If you see this picture, this might give you a little bit better idea that this is how it looked like. So there are multiple devices in the data plane or in the forwarding plane, and there is one controller in the control plane. This controller is managing all these devices. Now, how can this guy be able to see what's going on in the entire network? It gets the intel out of the switches. So intermittently, the switches will be forwarding the network traffic condition to the controller. And based on those statistics or those information that is shared by those switches to the controller builds a global visibility that this is the current network traffic conditions inside the software-defined network or in the data plane, right? So let's say if there is a congestion going on here, these two switches might be reporting that our delay, the latency that we have incurred during the forwarding is this, which does not look normal. That means the SDN controller would guess that there might be some congestion going on. Okay, so all the statistics or the flow statistics or the network statistics being collected by the controller, and that helps the controller to build the global visibility of the network. Now, the same thing, this global visibility that the SDN controller gets out of the network infrastructure, it shares this information with the application. Okay, application does not need to know in details what's going on, but if there is some idea that might help the application to route its traffic better, it would do that. Okay, so with the help of the SDN controller, the applications becomes aware of how the network architecture may look like, what are the current conditions of the traffic inside the network. Okay, there's one more thing that I wanted to mention here before moving forward, that this SDN controller is not a single entity. In most of the big network, what happened, there are multiple controllers, and each of the controllers is responsible for only a section of the network switches, okay, or the network infrastructure. And there will be multiple other controllers, they will be responsible for their own segment of the switches. And these controllers do exchange information about the network statistics, because they have no visibility in the other section that's mapped to a separate controller. So they should be sharing some information across them to have an idea of the entire network. Okay, and how the routing happens. So anytime a new flow is starts sending or initiated, it starts sending a new application, is started sending a flow, what happens, the packet reaches the network or some of the switches. So if there is already a rule established for that type of, so let's say what they're going to look for is priority. So let me draw something here. So let's say this guy has something, a table like this, which will say like priority, I'm saying PR, and the port. Okay, so if the packet has a priority 1, then this switch should send it to the port number 0. If this switch receives a packet with priority 2, it should forward it to the port number 2. Okay, something like this. So the first thing this switch will do, it will try to look into the packet header to find out what priority it is. Okay, so if it has this priority defined, let's say the priority is 1, this switch would forward it to the interface 0. Let's say there is the interface 0, interface 1, and the others. Okay, so it would forward it to this direction. And there might be some other rule which say if there is nothing established, then just forward to the port 3 or interface 3. So anything other than 1 and 2 priority should go to the interface 3. So that's what it's going to do. Now, if there is something that came with a completely different, like priority, let's say, I have said a catch-all. Let's say we define something else. So it has a priority, which is 0, which is more than 1 and 2. So now it has no rule set for the priority 0. So it must be a very, very high priority packet. And this guy does not really know how to forward it. So what it's going to do is it's going to send that packet to the controller. So controller will look into the packet and will see there is a new thing that came. I have no clue what to do. So it will find out the rule that is appropriate for that packet. And that rule, it is going to download in all the switches that it is responsible. So it will update the flow table of all the switches with that flow rule, so that no switch should be able to ask the same question. So everyone should know what is going on, okay, or what to do the next time it sees this. Let me see if I can erase this. Okay, so this is kind of what how this routing works. Anyone having any question before I move on to the next page? Okay, if not, then I'm going to talk about what are the differences here. One of the biggest differences is the separation between data and the control plane, right? They're completely separate entity in the SDN, whereas in the traditional network, the network infrastructure or the switch or router they do both the control function and the forwarding function. So they have to decide which way to go, and then they also send the packet. Okay. In SDN, there is the control is centralized. There is only one controller that makes all the decision. In traditional network, it is distributed. Now comes the programmability. So what is the programmability? So if, let's say, there is some congestion going on, or some links broken, some switch is not operational, the switch failed. So the controller will see that and quickly identify that something went wrong. So the controller can change the flow rule inside the flow table of the switches in the runtime, which helps in rerouting the packet without causing any drop or delay, or like there would be some overhead added while you are making those changes, but it can be done like while the flow is ongoing, right? Whereas that really does not happen in the traditional network. You have to set this information statically. You might have to run some additional algorithm to find out which way this would go. So it's more like manual and static configuration. Okay, so that programmability we're referring as an auto configuration. So if anything happens, the controller is very fine to get into this switches and change one rule with another, or update one rule, or insert a new rule. So that can be done dynamically. So SDN has a low cost and complexity because this is software, right? So all you are doing is you're taking hardware from any vendor, like you take the switches from any vendor. All that the switches care about to have an open flow support, or support for the open flow standard protocols. So you have to install that software on top of the switches, so that if you have a controller that running the code for SDN and it starts talking to the switches, then the switches should understand what language that this controller is talking to, right? So you have to install just software, that's all. Whereas in traditional traditional approach of the network, most of the time we call it TCP/IP network. In there, we have to make sure that the whatever changes that you want to bring should be built into the hardware, which costs you more. Here, you have a lot of flexibility. But remember one thing, that's I want to set the expectation correct, that if you are doing something in hardware, it will be possibly faster. If you do something in software, that will be little slower. But doing it in software will give you more flexibility, because if you change the program, it can adapt to different situation. It can take your instruction, whatever you're saying. So you have more flexibility if you're doing it in software than if you do it in hardware, because you cannot randomly change the logic, hardware logic, but you can change the software logic very easily. Okay, so that gives you flexibility, but that causes you more latency. Hardware logic gives you less flexibility, but it would be faster, and yet you have to remember it would come at a higher price tag. Okay. Highly extensible. This will be not extensible. This will be not that extensible. So what do you mean by extensible? So let's say if I want to extend the network, and I have yeah, this has been actually, I should change this. So this is not highly, this is not extensible. That is not easily extensible. And this is also harder to troubleshoot. Okay. So why it's highly extensible? Because let's say you want to grow your network. All that you care about is to bring in a couple of switches, install this open flow protocol or the software stack on top of it, and then just let that switch to be mapped to a particular controller. That controller takes hold of the switches, and your system or the network would grow eventually, right? It is not that easy for the traditional network. Why I'm saying easy to troubleshoot? Because of this central controller, because the central controller would try to build that global visibility, which keeps the global controller more aware of what's going on in the network. Then you're having zero knowledge of why the packet being dropped somewhere in the network, or why the packets are getting delayed, or like anything that happened to the network. Okay, any question? So this is where we are going to stop discussing about the infrastructure and the details of the SDN, and I'll move more towards the traffic management, where we are going to discuss about the challenges in the traffic management and sort of the approaches that we have, and the areas that we can address in the future. Any question? Okay. If not, I will move forward to the next slide. Give me 1 second. Okay, so what is the pros and cons of the traffic management in the SDN? Definitely, we have already talked about it's a highly flexible in terms of architecture, and the like extensibility is very good. Dynamic configurability, if there is something that comes to the network and new, the controller can take care of that very well without causing any problem. It supports developing different network functions. So there is something called network function virtualization. So it's very easy to really run those functionalities on top of the controller. So let's say you want to run some traffic management. So that is going to look through your network and would see like if something is getting dropped, it will give some management metric, some application that you want to run. So all that you need to do is you have this controller, right, which can access all your switches. So all that you care about is to create a virtual machine that will run those application, and you would plug it with your controller. Okay, it's that easy. So you can run any number of application very easily. Okay, so it can like you can develop any kind of network functions using that controller interface. And I have already said, like, you can buy like you do not have to buy specific network devices. Like all you care about that all your network devices should support the open flow protocol. Now comes the cons. I would not say again as cons. These are like the opportunities where we can do better. One of the biggest problem that why we use distributed system over any centralized solution is that the single point of failure, right? So you have a single controller in the worst case in the network. So what happens if it fails? Okay, we try to use a failover controller. So if we keep more than one controller and make sure if anything happens to this controller, we dynamically move this control from one controller to another. That's what we do. Okay? But otherwise, this like handover time from one controller to another controller is quite a bit, which causes the application performance to drop, and the application could see that something is going on which is not right. Okay? So whatever you do, it shouldn't be visible to your application that's running inside your network, right? So that's the target. It's prone to attack, obviously. First of all, you are trying to make the switches dumb. So switches does not really use their brain, which is bad sometimes, because if you allow them just to forward, they will forward anything, literally, right? So you don't want that to happen, because they can forward malicious packets. Even though they are malicious, they're not going to look into it. So that's a con, right? The another thing is if it is a central controller and you can put that down by attacking it, then your entire network is down, right? You may think that, okay, there are certain flow rules that will be there in the switches, so the switches should be able to perform. Yes, they would be able to perform for those established flows or those flows that they are already aware of, but anything that new that comes, the switches have no clue. So they will just dump those packets or drop those packets and would not forward them. Okay, so if you can attack this controller, the central entity, you are done. You very well can take the whole network down. So it's very common to have this type of attack like DDoS, like distributed denial of service, intrusion, spoofing. Those are very common in case of the SDN. And you will see a bunch of papers, and still the research is going on. We would see like this is a very hot area of discussion. High energy consumption. This is actually true for all the networks infrastructure. What I'm going to highlight on is why this is interesting in case of SDN, that we can do much better in terms of energy consumption with the SDN, okay, which is not possible in the traditional network. Traffic congestion is possible because at any time, and that's the thing that this denial of service attack has, it starts sending the controller a bunch of packets. So at any given time, the controller start getting a lots of packets. A single controller, just think of it, it's going to process every packet that it is getting, and this is a single person. Like if you are sending me thousands of assignments, so I still have to grade them, right? And at a like real time, I will be overwhelmed. And that's what happened with this controller. So if the controller is getting a lot of messages, lot of information, or a lot of requests from these switches, then you will see a congestion going on, right? So there could be possible congestion in the forwarding plane as well as a congestion at the controller. That's possible. Okay. Then is the performance problem due to imbalance. And what is that? Let's say we said that there could be multiple controllers in the networks, right? So it's possible that if you do not design your network properly, there will be some controller which will have very large number of switches that they are controlling versus some controllers which will have fewer number of switches, right? So if there is that disbalance, you will see there are hotspots. Like some of the controller would be overwhelmed where others are just sitting idle doing nothing, right? So there will be a performance issue due to this disbalance. And we want to do the load balancing properly. So these are the 4 sections that we are going to talk about: is attack, energy consumption, congestion management, and load balancing. Or we call it, like the last one, we actually call it controller placement problem, like CPP, where we try to place the controller first in a part of the network which is the best for the controller, and we'll then try to map balanced number of switches to the controller so that the controller can do really a good job. Any question? Okay, if not, I will move to the next, where we are going to talk about the solutions to this. Okay, the first problem that we are going to talk about, so these are the broad solutions that I have tried to draw here. So single point of failure, to battle this, we would use a failover controller that I have said, like if some controller fails, we will put that responsibility on the other controller, which is a standby person there. Then prone to the attack, we have to use dynamic security enforcement. That's very, very important. Like you have to, on the go, you have to realize that something malicious is happening and you have to act on it. Okay. Also, you might have to proactively define what the threat look like. Okay. Because what does attackers do? They try to change the behavior of the attack, right? So if something is completely new and you are waiting to learn from your past experience, you may not be able to see that, right? Because you may not have seen that type of attack before. So you have to somehow build the intelligence on the go and take action. So you have to proactively detect and prevent various attacks as possible. Okay, and this is a very open area again. People are exploiting AI in section to try to understand if this packet, let's say if a packets come, if this packet is with a fake IP, it's trying to do something like eavesdropping, it's trying to learn something from me, it's going to exploit something. So those are all the things that people are working with the security of the SDN. High energy consumption, the solution is to use sleep mode. I'm going to show how that works. Traffic congestion at the controller. So if there is a congestion going on, we have to adapt to some load balancing technique, how we can balance the load. And finally, for the performance problem, where we said like some of the controller to switch mapping is not appropriate. In that case, we have to use some controller placement algorithm that is even, and we'll try to do justice to all the controllers. Okay. So the first thing we are going to talk about, I believe, the load balancing. Okay. And we are not going to talk about the data plane related challenges because that's kind of straightforward. What we're going to talk about is controller related issues only. Okay, how the controllers handles the load balancing challenges and what are the results of the load imbalance. If you have a load imbalance that the controller is kind of getting a lot of hits by the switches, you will see there will be packet reordering, there is end-to-end delay, increase in latency, and service unavailability. Like if you are making a controller overwhelmed, as a result, you would see the controller is not able to perform, right? So after a certain time, when it's getting more and more job queued up, eventually you'll see that some of the new requests that are coming, they will be sitting long, like in the like tail of the queue after thousands of requests, right? And then what's going to happen, this guy who has sent that request will think that, okay, then the controller must be down because I'm not getting a response, and it's quite a while, right? So the service seems to be unavailable, so it will result in service unavailability. So that switch will say, never mind, I will just drop the packet because I'm not getting a response. And there should be some agreement within which the controller should respond to the switch, right? So when we select a load balancing technique, we have to take into account these criteria. Important things are like network size. How big is the network? Okay. If it is a couple of switches versus a couple of thousand of switches. What is the latency requirement that we have? Okay. So for example, we have to see like what is like what I said about the agreement, right? So the controller should clearly state after or within what time it should get back to a switch with a reply. Okay, there is some turnaround time or latency requirements. What are the type of traffic that this network handles? So if it is a streaming traffic, or it's a kind of interactive traffic where this is an application where the user is interacting with with the software and or a server, and the user should not see the delay, right? So if it is an interactive application, then the latency requirement should be very, very stringent, or any convergence requirement, like if there is any. So those are the things that we have to keep in mind while selecting the load balancing strategies. Also, we have to make sure it will be adaptive. And that's why, like, all of the solution that you will see in the software-defined network infrastructure, that comes with a tag of adaptive control. Okay, that means the controller will be very aware of the network situation and can dynamically change the rules, the flow forwarding rules, the policy, or whatever that's needed to adapt to the situation. Okay, so that dynamic or adaptability is the USP for the software-defined network. Okay. Now, there are approaches we call centralized versus distributed. So what is the centralized approach? So what happens? So if there will be one controller in the network which will be looking throughout the entire network. Like there could be multiple controllers, but there will be one which is responsible for this approach, and it will just run some algorithm to collect statistics, and it will look through all the statistics to see if there is any other controller in the network is getting overwhelmed, or it's getting a lot of interaction, and it's not able to handle everything right. Then what it's going to do is it's going to shift that load from that controller to another controller which is lightly loaded, right? So that migration it would do. Now the problem, again, it's not that scalable. So if you have only 5 controller in the network, and that one of the 5 controller is dealing with this algorithm, then it's kind of fine, right? But if you think of a network that has 15 controller, and there is one controller out of that 15 is designated for this role, then that controller would be overwhelmed again, right? Because this guy has to do this, the whole task, right? So that's a problem. So that's why people started talking about the distributed control. So most of the time what happens that there are like multiple controllers, and they, like, most of the time what happens is all the controllers actually takes part in this, and they will inform the other controller about their current states. So for example, if I am my controller capacity is running at 70%, I'm fine. But if it goes beyond 80%, I have to let the other people in the network know that I am getting really, really busy. So I need to transfer my load to someone. Okay. So that is a distributed approach. And they would continuously either receive those kind of messages, which is again not that a good idea, because you know that when you are sending these messages, you will be using the network links and stuff. So you need some network usage for that purpose. So to avoid the situation, sometimes what happens is there are a couple of threshold and these threshold based techniques are used. For example, you will set up a couple of threshold, like 50% then 70%, then let's say 90%. So if some controllers is in 50%, and the next time it checks itself, it's still in the 50%, it does not share the statistics, right? And the other parties will know that, okay, the last time it repeated or it let that controller forwarded message, it said that I'm at a 50% utilization. I do not see any other message, so that is the latest utilization might be. So the controller will only send a message to its peer when it reaches to the next level or falls to the another level. So if it is below, let's say 30% or 20%, it will let the other know that I'm in the different threshold category. I'm no longer in the 50% grade. Or if it reaches to the 70% grade, like somewhere between 50 and 70%, it will let the other know that, hey, my utilization is picking up. Okay, so it only circulate that message occasionally under certain conditions. So there are different ways that people have proposed this. In one of my paper, what we did is we used a couple of thresholds to kind of determine whether to migrate or not. So when let's say a controller is running at 50% utilization, we would just observe and we'll hold on to the migration. We would not do a migration. Or sometimes people do, like, we only do 1 or 2 migrations. Okay, and then when it reaches to 70%, we might be doing 5 migrations. So we will limit the number of migration. When I say migration, it's we are migrating my responsibility to another controller. Okay, so when I do that, that controller will be responsible for those switches, and that's kind of a disruption for the switch function. So we have to be very careful that when there is ongoing flow, the switch is handling those flows, and we are migrating this load from one controller to another, it can cause severe disruption if it is not planned properly. Okay, so also there is one thing that some controller uses response time based. Like if there is something that is getting delayed for longer, they would think that something is going wrong, so they would migrate to another controller. Anytime when you do this load balancing, you have to keep in mind about the ping pong effect. Okay, so you do not want to do a drastic change that will cost you to have another congestion at the target. So you are taking some load, you are moving into the target, right, to another controller. Now that controller has a lot of things on its plate, right? So it can be congested again. So what you would do, you would take that from that controller and you move to another controller, right? A third controller. You can overwhelm that guy too, right? So when you do not want to do this, okay, and then the third controller might be overwhelmed again and find out this first controller is the one that is not doing much, so you will go back to this. So it will have this ping pong effect. You will go back and you will come back again. So you don't want to do that. You want to avoid this kind of situations. So you have to be very diligent while doing the migrations. Also, there are certain approaches. So this is what we do when we look from the controller's perspective, what the controller has. Like if the controller is overwhelmed, if the controller is saying, I have a lot of things to handle. But if it is just the controller, sometimes we do not have the proper intel. So we can also take into account the link load. Like if there is certain links in the network that is overloaded, then we'll try to move out some flows from those routes to some other route where the links are comparatively less loaded. Okay, we call this hybrid approach because we consider both the controller's ideas, like what the controller thinks it's good to do, and we also look into the network links to see what is the utilization of the links. Okay, any question anybody is having right now? This is from just for the load balancing I'm asking. Anybody wants to have any like doubts or want to ask any question?
I have a quick question.
Yeah, go ahead.
So when you migrate the flows, how long does it take to actually update the flow tables and to actually, propagate that through the network so that the controllers know that, okay, from now on, this is the new controller that's going to be processing the flow? And then how does that affect performance?
Yeah, it does affect performance, first of all. Okay, so it cannot happen in zero time. The controllers will try to minimize the impact as much as possible. So what they would do is they will going to create this entry in the new control, in the new controller. And let's say if you want to move a flow from a path directly, right? So you want to reroute the flow to a different path. So what you have to do, you have to wipe off all this routing tables or flow information from the flow table of the switches and update it with something new, right? And then you have to still send all the existing packets that the switch has using the current path that the switch is using. And then from anything that it gets new now onward, it will be using the new traffic rule, right? So it can be done in different ways. You can set a timer to the last entry that after this much of time, this entry will be stale, and that's how you set up the expectation for the switch. Or you can directly go and take that information out and put a new entry in that place, which will cause the packet drop, may cause a packet drop, because you now at a point you may not be able to forward in the right direction because you have changed the route altogether. But honestly, it really causes some traffic disruption, and it is to be handled very nicely, I would say.
Thank you.
Mm-hmm. Yeah, but there are multiple approaches you'll see in the literature too, which tries to handle this nice or clean hands-off, like how you should move from one controller to another controller, or even like you want to move from one link to another network link migration. Okay. This is about the energy efficiency, what we have talked about. I have said that the network links and the network, all the network infrastructure ports and switch backplane, which is very energy hungry, all of them cost a lot of power. Okay, they consumes a lot of energy. Now, what is the difference between the traditional network and the software-defined network is the key player here that allows you to save energy. Okay. Now, remember that this energy efficiency is not just the energy consumed by all this infrastructure. It's beyond that. What we do not realize that there is an HVAC or the cooling infrastructure in the network that cost a lot of energy. Like if you look for a data center, you will see more than 50% of the energy being spent for cooling the data center, right? So you have to run air conditioning, water coolant, or whatever, the entire infrastructure to run it and to cool it down. It takes 50% of your energy, right? So what if we can turn off some sections of the network when it is possible, right? So that is not possible for traditional network, or it's possible, but it comes with different challenges. But this is much easier in case of software-defined network. You may be curious to know that like many of the data centers, that's why built around the rivers, where you can get free water, free cold water to run along the warehouse, or where you have this infrastructure built, and you can cool it down for free. You can have river water as much as you need. Another interesting fact for this is, if you think that if the network is not under use, it is not communicating any message, it's not wasting energy. Actually, that is false. It's a synchronous link. All the links are synchronous. So basically, even though they are not sending real messages, they are still sending some symbols so that they are on sync at the receiver and the transceiver in one switch versus another switch are on sync. So they keep sending messages, even though they are not meaningful to the the recipient. They keep sending those messages to make sure that both of them are alive, they're on sync, and that's why it consumes the same energy whether a network is in under use or not used. Okay, so that's why we proposed certain energy management technique for SDN. So what you are capable of, like IEEE, there is a standard 802.3, which is called low power idle. Okay, that means you can put your links in a really deep sleep mode. So you see this picture here you will see, let me see if I can change it to leisure. So if you see here, this is where we are transmitting the packet. So the packet gets transmitted and then there is nothing to send. So again, we have a packet transmitted and then the link is idle. Idle means it's still consuming the same energy. It's not just sending the data. Okay. Now, what we are going to do is so sometimes, like most of the time, idle is like 10% less than the 100% energy consumption. Now, if you can put it to the sleep mode, so we will wait for some runway. Why we wait for the runway? We just want to make sure that nothing is coming. Okay, so we have waited enough before we can transition to the sleep mode, because the transition to the sleep mode and coming back cost you a little bit of time. Okay, latency. So you want to put your infrastructure to sleep mode, deep sleep mode, and then when something comes back or some traffic comes back, then when you start to wake those devices up so that they can start the communication. Okay, so this is how you can save a significant amount of energy. Now, how we can increase this opportunities of infrastructure can go to the sleep mode. That's where this software defined network comes. So we can, the controller can see what are the flows that are ongoing. So if you see this picture, these are all the switches and these are your endpoints where your applications are running. So what you can do is, let's say this guy can forward the packet to this direction as well as this direction, right? If you see this picture, so these are the endpoints, these are the switches. So if this guy wants, it can forward the packet in this direction as well as it can forward the packet to this direction. But if the controller sees that this device is using this link and this switch, so if a next flow comes, the controller would try to use this path, not this path, because if you use this path, then this switch has to be active and working, and this switch is already active. So it will try to consolidate the flow to the minimum number of switches, okay? So that this switch that you see now can be put into the sleep mode for a long time. And the controller can make the decision dynamically when making the dynamic routing decision. Okay, so if there is an existing flow ongoing at some switch, then the next time when a new thing comes or a new flow comes, then the controller would try to consolidate the flows so that minimum number of switches or the network links will be in use. Now, see, there is one challenge with energy management, and anything that you do around the energy, you will see there was a performance cost. So let's say if you would have forwarded along this route, you would see it would be traveling faster because it would not be competing with multiple flows, where it is now competing with more than one flows, right? So if you are consolidating multiple flow along a fewer or handful number of links, you have better opportunity to exploit the sleep states of the devices. But the problem would be you may be in a spot that create a little bit of congestion in the network. Okay, so it's a trade-off between the performance and energy saving, like how far you want to consolidate and like pay for your performance. So there should be a balance. So you start consolidating your traffic, you go to a point, you see that it's almost very close to the onset of a congestion, you would stop there. Okay, and that's the point you should stop, which is an optimal point where you have the maximum energy saving for the best performance. So we call this intelligent traffic routing, which is a part of the energy efficiency, or EEE, energy efficient Ethernet, we say. For that, we use the intelligent routing. There is also the application space, like placement. This area is heavily explored, called BM placement. So what you can do, if there are two applications that wants to run database, and you can run it here and here, you would rather be running it here because this guy is already in use. You do not want to go to a completely empty section of the network and run that. So that is the way we do the VM placement. So there are intelligent ways of consolidating application towards one side of the network versus others. Okay. So we have to make sure whatever solution we are proposing, it has to be scalable. So it shouldn't be something that needs a lot of statistics to be kept before it can make a decision. So it has to be scalable. It should be fault tolerant, cost effective, definitely. And the computation time is the key. So you cannot spend a lot of time deciding what to do. Okay. So I have 2 more slides. If everyone is okay with, then I would go to those discussions because I'm almost at 10:30 right now, or 8 o'clock of your time.
Yeah, sure, ma'am. You can take more time.
Okay, thank you. So this is about the placement problem that I was referring to. So given you're having a network and you are starting afresh, so nothing is there in the network. So what is the designated place for the controller? That is one thing that you have to decide. And how you want to map the switches to the controllers, right? So there are many questions around that that we have to decide before you design the network, right? And this is kind of a static problem. You can do it before bringing your network up and running, but these are kind of the question we address under this CPP, or controller placement problem. It's a big problem. People have proposed many solutions. Nothing really works that well, I would say, but you can come up with a solution because this is, as I said, is more of a static problem. So how many controllers do you need for the entire network to cover the network reasonably? How many controllers that you need? You have to think about the cost. You cannot get rid of the cost. You also have to think about the latency. So why we need more controller? The best thing, you need one controller that can look after all the switches in the network. It will have the global visibility. Problem, definitely the single point of failure, but beyond that, you will see unfair treatment. For example, if a switch which is located quite a farther away from the controller geographically, then that has to travel longer to reach the controller than a switch which is closer, right? So you do not want that to happen. Okay, that is a fairness issue. So to break those barriers, you have to create the multiple controller situation where you have no multiple controllers, but now you have to answer this question: how many controllers? Where exactly you want to place them? How many switches you want to map to each controller, and how this migrations are the migration from one controller to another controller happens when one controller fails. Like when one controller fails, how the switches that are mapped to that particular controller would be managed, and who is going to manage, how the decision would be made. So there are more questions than answer. Okay, some of the approaches that we have seen, like they will start with a number of controllers. So you may start with, let's say I have 5 controller for this 500 switches and I want to place this 5 controller. That's a different problem versus finding out how many controllers that I need for this many switches, and then also find out what is the optimal placement for them, right? So it's a very complex problem. Most of the time, to define all this, like to give answers to all this question, you have to build a multi-objective optimization, because what you are looking at, you have to reduce the latency, you have to keep the latency minimized for all these switches, so that the switches should, while communicating to the controller, it should not spend a lot of time. So that's the primary objective of your optimization. You want to minimize the delay. Cost, you do not want to create unnecessary number of controllers. In the best case, you will create multiple controller and map it to individual switches, right? You don't want to do that. That's a complete waste. So you want to keep the total number of controller minimal, which is the cost reduction. You have to reduce the load. That means no controller should or no section of the network should be overloaded. So you kind of want to distribute it. Also the capacity of the controller. So if the controller, given its memory, its processing power, it can handle this many switches at a given time, it should not be given beyond that, right? Responsibility beyond it. So all would be the part of your optimization objective. Challenge is that most of the time when you're solving this problem of finding out the total number of controllers, that programming result into integer linear programming, and we solve it using either approximation algorithm or heuristic, some sort of greedy heuristic that we use. You'll find out some papers that have used like particle swarm optimization or simulated annealing in some cases. So they use a varieties of optimization technique to find a solution to this. Okay. And as I said, like the challenges, first of all, it's a multi-objective optimization, and it's almost in the very most of the cases, I'll say it's NP hard, so you have to use some sort of heuristics. Okay. But this is the latency is a factor that drives this problem. So this is a primary focus that you should look for, is what is the latency look like for the switches to the controller. Okay, now the network threats. So what are the network threats? So you can have network threat at the control plane, that the denial of service, distributed denial of service. So Microsoft came with a standard called STRIDE. It constitutes of different types of attacks, so called spoofing, tampering, repudiation, information disclosure, denial of service, elevation of privilege. So all these kinds of attacks are part of STRIDE. But there can be, like, the attackers are very innovative, so they come up with different challenges, and the easiest part of it is to take down the controller and your network will be down, right? So it is also possible for controller hijacking. So for example, I will impersonate or some attacker will impersonate as a controller, and it will start to flood the flow table with improper routing information. Okay, so it will exploit the vulnerability of the controller during the build time. So when you are creating the controller, you are injecting those codes inside the controller. So it can happen during the build time. Also, it is possible during the forwarding time. So when the controller is about to send a message to the switch, it can inject some weird malicious information inside that. Okay. Now, so you will see a lot of activities exploiting AI in the section, right? So you will see that the controller would capture all this information from the past attack, and it will try to build some ideas based on what type of feature that you will see for those packets. What are the headers or the informations in those packets look like? And they will build a knowledge base out of it. So the next time it receives some communication around that, it will just discard this packet, okay? Or it will set a rule inside the flow table which says that if you see this criteria in a packet, then just drop it. Do not forward. Even do not forward it to me. Data plane has a different set of attacks. You'll see it's not as bad as controller, but it still has like denial of service, distributed denial of service, like it will be, so distributed denial of service, and then the spoofing attack. The problem with the data plane is if you can, so data plane switches are the first entry to the controller. So if you can capture one of the switches, they do not use their brain, as I said, right? So they just look into the flow table and forward the traffic. So if you can somehow influence them to get to the controller, they will go to the controller. They will start sending all the dumb messages or those malicious packets to the controller, right? So if you can get hold of the switches, you are going to get the controller. Okay, that's the easiest part. There is also, we call a southbound attack and a northbound attack. So if you go to this picture, this is, we call a northbound interface where the application communicate to the SDN controller, and this is the southbound interface. So you see this open flow. So this is a standard protocol that is used, which is open flow. For this communication, any programming can be used. Okay, there is no standard set for it, and that sometimes make it vulnerable. So you can do man-in-the-middle attack, black hole attack, intrusion. One of the things you can do is you can see the communication going on between these two interface, between the controller and the control plane and the data plane. You look into that, you'll see what's going on, and you take that information, collect whatever information is needed, and then you start exploiting those information. Like if you see there is a gap that you can attack or you can use in your attack process, then you would use that. Okay. In an outbound traffic, you'll see intrusion, that most of the time the application will start injecting malicious code. So that's why one of the way they try to stop it by using all the application developer has to use a unique user ID and a password. Most of the time, it's mostly encrypted authentication that they use to make sure nobody other than the authorized persons are injecting any code from the application layer to the control layer. Okay. These are a handful of approaches that we use. First of all, we can use controller authentication, that every time the controller want to give a rule to me, to my flow table, I have to make sure that this is a controller which is authenticated by any encrypted algorithm, like some of the identities that it has to use for that authentication process, during the authentication process. There are other things that I said, like the controllers may use to authenticate what to do with the packet if a packet is coming. For example, if it builds a trust score, like if it tries to keep a note of what kind of packets it's getting from its different switches, it will build a trust score based on that information. Okay, so I trust you. If I give you a trust score of 1, that means I trust you the most. If I give, let's say, a trust score of 10, that means I do not really trust you that much. Let's say I'm just giving an example. Now, next time you get a file, you get a packet from a person with a trust score less than 10, I would rather be not entertaining the packet. That's kind of what they do. As I said, if there is an intrusion happening, so the controller would just discard any malicious application that coming from the application layer. It can builds a repository or a knowledge base out of the existing attack, but the challenge is, as I said, the attackers are continuously modifying this knowledge, the type of attacks, the patterns of attacks, so it becomes very challenging. So the last thing that I was talking about is the reinforcement algorithm, or the kind of game theoretic approach where you use this continuous learning approach to learn what kind of attack is happening, or is there anything in this packet which looks fishy, or which from my past like interaction with the packets, I know that something went wrong with this kind of signature. So those are the thing that is currently under kind of the recent work you'll find more often. And yet I'll say it's not extensive, so you still have a lot of scope around this area to exploit both your AI and to battle this SDN threat. So that's kind of concluded my talk. There are other open challenge areas. It's kind of a never-ending process. There are caching at the SDN controller, at the switches. You'll see the flow tables are getting bigger and bigger. So you would see there are problem how to handle this flow table, because they store a lot of statistics. It's kind of a stateful solution, not stateless. So for traditional network, it forwards a packet, it does not really count, and it just takes every packets independently, right? At the forwarding level of forwarding, maybe at the application level or the TCP, it has this connection oriented behavior, but at the low level, you do not have this knowledge, right? You treat each individual packet independently. But SDN is more like a flow oriented approach, where you keep the information very detailed, and you collect the statistics over time. So your flow table would grow very fast depending upon your network size and utilization. So there are many problems that comes with that: performance, reliability, caching, scalability, and how you want to manage them. So these are the things that you can still look for, but I thought to just emphasize on those 4 things. Sorry about going over by 15 minutes pretty much. And I'm open to take any question if anybody has.
Hello, thank you for your presentation. I have a question from the implementation part. So currently most researchers, they are implementing their ideas in simulation in SDN. We don't have much SDN related experimental test bed. So mostly one of a simulator called Mininet is used for evaluating the experimental setups and results. So I'm happy if you share some idea for the experimental implementation and evaluate the result in real experimental test bed or whatever you have used for your experiment. I'm happy to hear from you how you are doing the evaluation.
Yeah. So thank you. Yeah, that's a great question. We like for the data center network infrastructure, it is very hard to kind of get the infrastructure. So I have used Mininet personally, and then as you said, like most of it is simulation. So I have used NS3, I have used Omnet for the same, but it does not really run the SDN infrastructure or SDN protocol suite. Like I have used TCP/IP, and for some of the work I remember I built a different library altogether, so that to implement all the functionalities, not all, I would say the functionality that I need for the SDN to be functional, but it's in simulation. For the real life experiments, I remember we did an open flow virtual switch, if you know. So on the server we implemented that, and on the switch so there are only I think 2 or 3 switches in our data center at Temple University, where I did my graduate degree from, and we did build a network over there with a very small scale with just a single controller and couple of switches. And that's how we did some of the experiments for the congestion control stuffs.
That's good. Thank you. And with regard to implementation, when we take Sri Lanka,
Hmm.
we don't have much implementation in SDN stuff. We don't have any campus network running in SDN based architecture. But uh, uh, do you have any idea about other countries like developed countries, how they start the
Yeah.
implementation?
Yeah, I think for our purpose, so how it worked is one of the professors in the college, they got a fund, research fund, and it's not that the entire computer, like the university network, is running on SDN back then, because it was experimental and nobody wants to completely shift it from the standard TCP network to the SDN overnight. It's a lot of risk. So what we did instead, so they bought some servers and some switches. So we as a student we tried to build that network locally at a small scale, so that we can run our task on top of that network. It was not a network that's something like also carrying the external load from the or traffic from the university. It's just for our experiment, I can tell you, and it came from the professor's funding.
Ah, good information. Thank you.
No problem. Any other questions? Was it like easy to understand at the level, or I was just like very skeptical on what I should talk about and how far I should delve into the details, so that the students should not feel that they are off the topic completely.
Madam, there's a question asked during the pre-registration.
Okay.
According to that, they're asking for a little more explanation as how does SDN traffic management mitigate the risks of distributed denial of service attack?
Okay. So it's like being staying informed. So in the distributed denial of attack, what happens that you start sending these malicious packets to the controllers, right? And in case of the traditional network, it's harder to know right away what's going on. But in case of like the SDN infrastructure, it's kind of easier, because so how you want to do that is you are going to send this to the controllers, and the controllers, you would turn on the sync status as on, right? So that the controller has to reply, and the controller would get a lot of such messages, and eventually it would be overwhelmed, right? So how we want to battle with that is, if we have seen that pattern, like most of the time what happens, we capture the tags of the packet header, like these are the features that this kind of packets which I've never seen should have. And once we have that, we set the rule at the data plane. So you can really avoid reaching up to the controller. Sometimes what happens, so I've seen multiple solutions to that. One of the solutions which I really like is, once a packet that is forwarded to the switch that has those threads that you have learned from the past, you would just, the switch should just drop that packet. So it will try to match that, the knowledge base that you have built out of your past experience, and the switch will try to match, and it will drop. It would not even forward it to the controller. So controller would be completely kept separate from this attack. So you can right away stop the attack, which is not possible in the normal circumstances. I'm not sure the person who has asked this question is currently in the meeting, but if he or she can respond that, if he or she has any additional questions or comment around that, it would be easier. But that's how it's kind of handled, that most of the time you build this knowledge base. It's not knowledge base like you are looking for exact IP address or exact what should I say, exact priority or something, some unique information. It might be kind of a substring, something that was odd in the last attack. You would just capture those information and you will build the knowledge base. Okay, so you would then set it as a rule in the switches. So the switches will definitely going to drop the packet if it sees any of that matching pattern. So what they are going to do is to match an action, right? So if there is a match, they will drop the packet. Otherwise, they will either forward or send it to the controller. But for any malicious packet, they would never forward even to the controller to seek opinion, like what should we do.
Thank you, madam. With that, it seems like there's no more questions.
Okay.
And on behalf of the IEEE Women in Engineering Student Branch Affinity Group of the University of Jaffna, I would like to express our heartfelt gratitude to our esteemed speaker, Dr. Madhurima Ray, for sharing her insights with us today. And Dr. Ray, your comprehensive overview of net traffic management has undoubtedly enlightened us all and provided invaluable knowledge that will benefit on our academic and also research pursuits. And we deeply appreciate the time, effort, and the expertise you generously share with us. And dear madam, please accept the virtual token of appreciation we have prepared
Thank you.
as a small gesture of our gratitude. And I would also like to extend a warm thank you to all the participants who took the time to join us tonight. And your active participation and engagement have truly enriched our discussion and made this session a success. And the Women in Engineering Student Branch Affinity Group of the University of Jaffna is now available on Facebook, LinkedIn, YouTube, and Instagram, where you can simply follow us and stay tuned with our upcoming events. And also, you can visit our official website for more details on future and past events. And as we come to an end of today's session, it's perfectly okay if you're unable to switch on the cameras, but we request everyone to join us for a group photo, as it would be wonderful to capture this moment together. Thank you once again and have a wonderful evening.
I also wanted to thank everyone who were here. I know this is a Saturday night, so not the best time to attend a seminar or webinar. I would be available for your question. If you have any question at any point in time, I would say, please share my email ID so the student can reach out to me.
Yeah, sure, ma'am, will do.
Okay, thank you. Yeah, it could be any other research area. It doesn't have to be SDN. So If it is aligned to my research area and you redirect the question to me, I'll try my best to help you out.
More minute. If anyone wishes to turn on your cam, you all can. Okay, so let's go on a count of 3. 3, 2, and 1. Say cheese. Okay, thanks.
Thank you.
Thank you.
Thanks. Bye, everyone. Take care.